Let's take a look at the methods of energy transfer. There are essentially three forms of energy transfer, and we're going to take a look at the just the first one right now, and that is the energy transfer by direct contact. And this is something that is done through a process called conduction. Energy, thermal energy, is conducted, or thermal energy oftentimes is said to have flowed from one object to another. Now, this is the direct thermal contact. So by direct thermal contact, most of that energy is transferred due to two possibilities. One is free electrons, or it's by lattice vibrations. Now, all objects will have the last one, lattice vibrations. But metals have a special property called free electrons. This is what allows metals to heat up so quickly, so much more quickly than other objects, and I'm sure that's something that you already know. Metals heat up very quickly, and other objects don't. That's because they have to pass their energy on through lattice vibrations. So in this case, the free electrons are able to move around because they are not bound to any particular atom. They are completely free to go anywhere within the substance that they choose to. This allows them to very easily absorb energy and also to transfer that energy to all parts of the object quickly. And this is something that occurs essentially in metals and then in a few other objects. Graphite, for example, also is a pretty good conductor of energy because it has free electrons. It can conduct electricity, and this is the basic concept. These objects which have free electrons and are not only able to transfer heat very quickly, but then also, as a result of those free electrons, they also are electrically conductive. So any object that is a good conductor of heat typically also is a good conductor of electricity. Those two things sort of go hand in hand. The second form of energy is something called lattice vibrations. And lattice vibrations are simply the shaking or the vibration of the atoms. And so the way this transfer occurs is much more slowly. And although all substances can do this, this is a very slow transfer of energy, because what essentially happens is one atom shaking hits into the atom next to it, and then that atom begins to shake more quickly. So if we, for example, imagine a substance with four atoms, and these atoms are shaking violently back and forth, and I put them in contact with a very cold object, which is just shaking a little bit. Now what I will find after time is that heat will flow from the hotter one to the cooler one, and eventually we'll see that everybody is shaking by about the same amount. So these guys shake a little less violently, and these guys shake a little more violently. Okay, so the guys next to them begin to shake violently because they are literally being hit by the guys who are on the hotter object. So now these guys begin to shake more violently. These guys ultimately hit into these guys. Now these guys begin to shake more violently, and it works its way down the line. This kind of vibration is something that you would notice if you put, for example, a frozen turkey in the oven and you left it in there for maybe 5 minutes or so and then pulled it back out. Now, even though the oven may have been at 400 or 500 degrees, the surface of the turkey might be a little bit warm, but you would find that if you went just a little bit into the turkey, it would still be frozen. And that's because these lattice vibrations are very slow. They very slowly transfer the heat inward towards the center of the object. And so it's very slow. Whereas if you were to put a metal spoon inside of the oven and took it out, the whole thing would be almost the temperature of the oven by the time 5 minutes had passed by. So objects with free electrons heat up very quickly, and objects which can only pass the heat on through lattice vibrations will tend to heat up very slowly. So metals heat up very quickly, and pretty much all other objects heat up much more slowly. Now, this brings up the concept of transferring heat by conduction. And so let's take a look at some example problems that you might see. And that is that we connect an object which is very hot with a metal rod. Metal rods are great conductors. and we surround the rod with an insulator. So what is an insulator? Well, an insulator is something that doesn't allow heat to pass very easily, right? So obviously these would not be made of metals, plastic, wood, glass. These tend to be good insulators. They do allow the heat to pass through, but in this case we're going to make this one a perfect insulator. So no heat will be lost through this. The only heat will be transferred through the object in this direction. Okay, so this hot reservoir and this cold reservoir, we're going to keep them at this temperature. That is to say that even though heat is flowing through the rod to the cold, what we're going to do is we're going to keep pumping in heat into this one to keep this guy at the same temperature. And as the heat comes across over to here, we're going to extract the heat out. So over here, we're going to continue to add heat. And over here, we're going to take the heat out. And that will allow us to keep the two reservoirs at their same temperature. Now what's going to end up happening then is the rod is going to have one temperature at this end, and then as you move along the rod you're going to find that the temperature is getting lower and lower. So this might be temperature 1, and over here is temperature 2. So graphically speaking, how does this look? So here's the temperature in degrees Kelvin. Here's temperature 1 and here is temperature 2. And what's ultimately going to happen is that at this full length, L represents the length of the rod. What I will find is that the temperature will steadily drop in the rod in a straight line until I reach that point where the rod makes contact with the cold reservoir. That is to say, the temperature inside of this guy will steadily decline until I reach this point. Okay, so that should be, I think, fairly easy for you to understand. The temperature slowly declines as we move down. Now, what you should think about is, how would the shape of this line have changed if I removed these insulators? Now in that case, all of the heat wouldn't get transferred to the cold reservoir. Some of the heat would be lost elsewhere, and you should think about how this graph will change as I take away the insulators and no longer am able to keep all of the heat inside of the rod or the two reservoirs. Some of it will actually escape. Now I'll leave that for you to think about how that will work, and we'll look at that in class. Now, one of the questions would be, what would it look like? So let's take as an example the same hot reservoir at temperature 1 and the same cold reservoir at temperature 2, but this time we're going to connect them with two rods that are equal in length. And so again, heat will flow. We'll insulate these. We don't want any heat to be lost from the rods. Okay, and so here we have rod 1, and over here we have rod 2. Now in this case, let's make rod 1 a poor conductor. Maybe this is made out of plastic or glass or wood or something like that. So, and let's make rod 2 a good conductor. And the total length is, of course, L, just like it was before, but the length of this rod is L divided by 2. In other words, the two rods are exactly the same length. So now let's make our graph and let's see how this looks different than it did before. So here's L divided by 2, And here is my total L. This is my length in meters. Here is my temperature in kelvins. Here's T1. Here is T2. Okay, so what's going to happen here is that the heat does not flow as easily through the first rod as it does through the second rod. And what this ultimately does, and this should make sense to you, right? If you put a good conductor on one side and a poor conductor on this side, the side with the poor conductor will have a big difference in temperature from one side to the other, right? So for example, when you wear your winter coat, winter coats are very poor conductors. They're designed to not conduct the heat from your body to the outside. So on the inside you may have a temperature of around 98 degrees Fahrenheit, but on the outside there might be a temperature of only 30, 20, or even 0 degrees Fahrenheit. A huge temperature difference. You're always going to see a big temperature difference on either side of the poor conductor, and on the side of a good conductor, you're going to see a very small difference in temperature. So this means that most of the temperature change is going to occur between these two guys. So here I would see a very large change, very steep slope, and then when I get to the good conductor I'm going to see a very shallow slope. Okay, so that should make sense. The temperature difference on either side of a poor conductor would be very large, and on the side of a good conductor the temperature difference would be very small. Now this is different than we had in the first case where we only had a good conductor. We only had a very good conductor in between here, and so the temperature difference had to go from the high temperature to the low temperature. But here we have the option of making this temperature change in different steps, and so as a result of that we see a steeper line between the poor conductor than we do on the good conductor. Okay, we're going to look at several examples of these problems, and again, you should think about how would this look different, how would this graph look different if I took away the insulators on the outside, these sort of perfect insulators that allow us to keep all of the heat inside of the rods.